Hello. In this video, and the one that will be following it, we are going to derive the Hückel energies for the cycloheptatrienyl cation, commonly called tropylium. Tropylium is C₇H₇ with a +1 charge, and it consists of a planar 7-membered ring that, because of resonance, has a delocalization of the pi conjugated system over all 7 carbons, which are numbered in this diagram. Because of the complexity of this system, the next 2 videos will be rather long. Because of that, we will try to save some time by covering only some concepts only very briefly to get a more step-by-step analysis and description of the nitty-gritty details. If you haven't seen them before, you can see up here, you can see previous examples of less complicated systems that we have gone through in more detail for the elementary steps. By the Hückel method, we have to construct this secular determinant where we have alpha minus the energy along the diagonal, and then between any 2 carbon atoms that are directly connected, we have this integral beta. As a shortcut, we are going to divide through by beta and then make the substitution that x is equal to alpha minus the energy divided by beta. After making this particular substitution, we have transformed our equation into this secular determinant. We're going to try to solve for x, and we'll have a possibility of 7 solutions, and those 7 solutions we will back substitute into this substitution to get the energies for the different energy levels of tropylium. The technique that we are going to employ to solve this particular system is a technique called expansion by minors. We are going to be able to reduce a 7x7 determinant into a linear combination of 6x6 determinants. Then we're going to be able to reduce the 6x6 determinants as a linear combination of 5x5 determinants, and so on. And since it's a 7x7 determinant, it's going to take us a while to do this. For this particular 7x7 determinant, we are going to expand using the first column. So the values in the first column are going to become our coefficients, and they are going to multiply a 6x6 determinant that we get by removing the first column and the first row. That gives us a 6x6 when we use the entry in the first column and the first row as our coefficient. Next, we use this 1 as our coefficient, and as we go along the column, we alternate the sign. So that accounts for the -1 here. And then the 6x6 determinant that it multiplies, we get by removing the first column and the second row, and that gives us this particular 6x6 determinant that we see in purple. We also notice that we have a series of zeros. Since we know anything times 0 is 0, we will not actually write out 0 times some particular determinant, and that will help save quite a bit of time. So the final entry that we have here is this 1. So we notice that we have the x is positive, then negative, then positive, negative, positive, negative, positive. So the coefficient here will be a +1 times the determinant that we get by removing the first column and the last row. And now we have this third determinant in green, 6x6. So we reduce the problem of a 7x7 determinant into this linear combination of 6x6 determinants. Now we have to take each of these determinants and expand it as a linear combination of 5x5 determinants. we expand the blue 6 by 6 determinant using the first column. So here's the x, which is our first coefficient. And our second coefficient is the 1, and it's minus because we alternate the sign. And it's all multiplied by this x, so that's why we have the x outside of the brackets. To reduce the purple 6 by 6 determinant, we're doing something very slightly different here. While we could expand along the first column, we are just as able to expand along the first row. And that is exactly what we're doing here. Notice in the first case, we remove the first column and the first row. So we get this particular 5 by 5 determinant. And then if we use this as our coefficient, which is a -1 because we go plus, minus, plus, minus, plus, minus, then we remove the final column and the first row and get this particular 5 by 5 determinant. We still have to expand this determinant in green, except we're kind of running out of room, so I put dot, dot, dot. So you notice that when we continue to write, we're going to put it up here. For the third 6 by 6 determinant, the one in green, again we're going to use our trick of expanding along the first row rather than the first column, because we notice that there are only 2 non-zero entries here, while we have 3 non-zero entries along the first column. Also, we keep in mind that we have this alternation of sign, plus, minus, plus, minus, plus, minus. So for the first one, we have a +1 as our coefficient, and then for the second non-zero entry, our coefficient is a -1. So in our next step, to tidy up the board a little bit, we're going to erase the original version in the expansion of 6 by 6 determinants, and we're going to be left with our expressions in terms of 5 by 5 determinants. In our next step, we are going to use the distributive law to simplify the expressions we have so far in terms of a linear combination of 5 by 5 determinants. So by applying the distributive law, we're able to tidy up our equation right now. And notice that each of the determinants is color-coded to show from which original 6 by 6 determinant it came. Now, something which will simplify our labor a great deal is to notice that this 5 by 5 determinant is exactly the same as this one, which is exactly the same as this one. And we're going to be able to combine them by adding together their coefficients to make a simpler expression. And what we're going to do to remind ourselves of what happened, we are going to color this determinant, whether it occurs here, here, or here. In the succeeding step, we are going to write it in red. Since this particular determinant has coefficients of x squared, -1, and -1, we're able to combine them as a coefficient of x squared minus 2 times this determinant, which now is written in red to remind us that we consolidated 3 identical 5 by 5 determinants. Now we're going to copy down the rest of the terms here for our equation. And now we've successfully reduced our problem to a linear combination of the smallest possible number of 5 by 5 determinants. We're going to proceed to now reduce these 5 by 5 determinants to a linear combination of 4 by 4 determinants. We expand the red 5 by 5 determinant using the first column. So our coefficients are going to be x and -1. I just put the minus sign to save some writing there. And it's all multiplied by this coefficient of x squared minus 2. To reduce the blue 5 by 5 determinant, we're going to use the top row because we notice that we only have one non-zero entry. So the coefficient here is going to be, say, +1, which we want to write there. And we notice that our 4 by 4 determinant we get by removing the first column and the first row. And we get the single blue 4 by 4 determinant. To reduce the purple 5 by 5 determinant. Now we're going to reduce by using the expansion using the first column, because we notice that there is only one non-zero entry. So now the 4 by 4 determinant, that it turns out to be the minor in this case, is obtained by removing the first column and the first row. We can expand the green 5 by 5 determinant now by expanding using the first row, and we notice again there's only one non-zero entry. So that reduces it down to this 4 by 4 determinant, and now we've reduced our problem to a linear combination of 4 by 4 determinants. In the next step, to make things a little tidier, we are going to again use the distributive law to distribute the coefficient and then combine where possible. Applying the distributive law to the expressions for the red determinants, we see now that x squared minus 2 times x gives us x cubed minus 2x times the first determinant, and then we distribute the x squared minus 2 times the minus 1 times the second determinant. The third, fourth, and fifth determinants are unchanged in this step. Now we notice that this red determinant 4 by 4 here is exactly the same as this 4 by 4 determinant. So we're going to apply the same technique that we did before, and we're going to combine these, and at the same time we're going to change the color, and we're going to change this to brown. Combining the first red 4 by 4 determinant and the third, the blue 4 by 4 determinant together as this brown one, we have x cubed minus 2x, and then we have another minus x here, gives us x cubed minus 3x times what is now the brown 4 by 4 determinant. The rest of the expressions, this red one here, the purple, and the green, we bring down without any further changes. In the next steps, as you might predict, we are going to reduce the 4 by 4 determinants as a linear combination of 3 by 3 determinants. We will expand the brown 4 by 4 determinant using the first column. So we see the first coefficient is the x, and then the second coefficient is the minus 1. You have to make sure that we remain keeping the coefficient of x cubed minus 3x in front. We expand the red 4 by 4 determinant along the top because we only have one non-zero entry, which gives us this expression. For the purple 4 by 4 determinant, we expand now using the first column, only one non-zero entry, which gives us this 3 by 3 determinant. Lastly, for this step, for the green 4 by 4 determinant, we cleverly expand along the top, where we only have one non-zero entry, which gives us this green 3 by 3 determinant. And now we've reduced our problem to a linear combination of 3 by 3 determinants. So we're getting there. In the next step, we're going to collect some terms and try to tidy up this linear combination of 3 by 3 determinants before we make the final descent to a series of 2 by 2 determinants, which we can evaluate directly. Applying the distributive law to this expression here, multiplying times the x, we get x to the fourth minus 3x squared times the first, brown 3 by 3 determinant. And then we distribute the minus sign to get minus x cubed minus 3x times this particular brown 3 by 3 determinant. And we're going to simply write down the remaining three expressions without change in this step. And we get our equation reduced now to this combination of 3 by 3 determinants. Below here, we are going to evaluate each of these 3 by 3 determinants so that we can convert them to some polynomial expression. For the first brown 3 by 3 determinant, we expand going down the first column. So our first coefficient is x, our second coefficient is minus 1, and we have these remaining 2 by 2 determinants. Well, we can evaluate 2 by 2 determinants on site, so we have our coefficient of x. This is x times x minus 1 times 1, which is x squared minus 1. Minus, and then here we have 1 times x minus 0 times 1. So this is simply minus x. So evaluating, we get x cubed minus x, which is x cubed minus 2x. For the second Brown 3×3 determinant, we're going to expand across the top because we only have one non-zero entry. So this gives us 1 times x1, 1x, which is simply x squared minus 1. Notice also that the red 3×3 determinant is exactly the same as the first brown 3×3 determinant. So that leaves only the final two determinants to evaluate. For the purple 3×3 determinant, we expand using the first column, just using the 1, and then we have zeros. So that reduces to 1x01, which is simply 1 times 1 minus x times 0, which is nothing but the number 1. For the green 3×3 determinant, we expand along the first row. So we only have one non-zero entry, which gives us 1 times 1, 0, x1, which is 1 minus 0 times x, which is simply, again, the number 1. So having evaluated all of the determinants now, we are going to substitute these expressions in for the determinants in our master equation and see what we get as a combination of polynomials. Now, substituting the expressions that we had determined, we had evaluated for the various 3×3 determinants here, we've written them in, and now we have to apply the distributive law, for example, and to evaluate this particular series of expressions and simplify the polynomials. So then x to the 4th times x to the 3rd gives us x to the 7th. X to the 4th times minus 2x is going to give us minus 2x to the 5th. Minus 3x squared times x cubed is going to give us minus 3x to the 5th power. And then we have minus 3x squared minus 2x, which gives us plus 6x cubed. So now we have to be very careful because we have the minus sign there. X cubed times x squared is x to the 5th, but the minus sign makes it minus x to the 5th. X cubed times minus 1 is minus x cubed, but the minus sign then makes it a plus x cubed. Minus 3x times x squared gives us minus 3x cubed, but the minus sign makes that plus, so that's plus 3x cubed. Minus 3x times minus 1 is positive 3x, but then this gives us a minus sign again, so that's minus 3x. We have the similar challenge here we have to be careful of, so we have x squared times x cubed is x to the 5th, but we have the minus sign, so that's minus x to the 5th. X squared times minus 2x is minus 2x cubed, but we have minus sign, so it's plus 2x cubed. Minus 2 times x cubed is minus 2x cubed. That makes it plus 2x cubed. And then we have minus 2 times minus 2x gives us plus 4x, but with the minus sign gives us minus 4x, which is right down here. And then we have plus 2 is equal to 0. Now we need to combine like terms. We notice that we only have one expression to the 7th power, which is x to the 7th. There are no x to the 6th, so now we need x to the 5th power. And if we add those up, we get minus 7 x to the 5th. There are no x to the 4th powers. As far as x to the 3rd power goes, we have plus 14x cubed. There are no x squares. We do have first powers of x, so we have minus 7x. And then our linear constant value is plus 2. So we've reduced the problem, after a great deal of labor, to the problem of finding the roots of this particular 7th order equation. And this is where we're going to stop for part 1. but I will welcome you back for part 2 to show how we find the roots of this particular equation and how we use those to find the Hückel energies for the tropylium cation. I thank you very much for your attention. See you back soon, and as always, have a good one.